Log on, tune in, find out. Another good idea from Cambridge.
Well, welcome to this last in our present series on the theme of beauty. For me, one of the most memorable talks we've had this term has been Frank Wilczek's lecture on quantum beauty, which concerned things which are about as small as you can get, and now we're going to the other extreme with things that are about as large as you can get. Now, as you know, we had planned to have Caroline Porco, but at the weekend she fell on the ice in the Rocky Mountains and was quite badly bashed and bruised and so on. And she's emailed us today to say that she's recovering well, which is good, and she's asked me to pass on her regrets to you. We are, however, amazingly fortunate to have another distinguished astronomer, Caroline Crawford, to speak to us about the science and beauty of nebulae. Dr. Crawford works at the Institute of Astronomy and Emmanuel College here in Cambridge. She was educated in Cambridge, and her research has been on the properties of massive clusters and very large radio sources, exploring them over a wide range of wavelengths. But she's actually known to a much larger audience as a leading public speaker and broadcaster on science and astronomy. And in this respect, if this respect only, Caroline Crawford is to astronomy what Geoffrey Boycott is to cricket. Who better to tell us about the science behind cosmic beauty? Caroline Crawford.
So this evening's talk is still going to be on the idea of cosmic beauty. And I've used it as an exercise to showcase some of the most spectacular and beautiful images from both ground-based and space telescopes, such as the Hubble Space Telescope. Now, I'm showing you these pictures because they're beautiful. And, you know, the odd ooh and ah wouldn't go amiss. I hope you appreciate them. But I'm showing you them because they're also scientifically very interesting. And even if you recognize some of these pictures, and I'm sure you will, I want you to look at them with new eyes. I want to teach you how to read the science that's going on in these images, what you're looking at, what the cosmic objects are, and how they interrelate with each other. And ideally, get you to understand the science behind the beautiful images that we're going to be looking at. So, let's start. So we live in a galaxy that resembles this one. It's a spiral galaxy, 100,000 million stars all held together by gravity. And the galaxy is shaped like a flat disk, or the analogy we sometimes use is two fried eggs stuck back to back. And if the egg whites form a big disk, and the egg yolks form a ball of stars in the middle. Now, in our galaxy, we live about halfway out from the center out to the edge. And this disk is traced by brilliant spiral arms. You can see this in this image, that they're lined by large blue clusters of stars, beautiful arcs around. And we live in a spiral arm just like this. So when we look into our sky at night and we see all those stars are part of our Milky Way. And in addition, we can see blue star clusters which live in the next spiral arm and within our own spiral arm of the galaxy. So, for example, clusters like these. Those of you who might be amateur astronomers may know of the Perseus double cluster, a little double cluster of stars you can see in the constellation of Perseus. If you've got really good eyes, you can see them with the unaided eye. Certainly very clear in a small telescope or binoculars. And these are bright because they're close to us. We're seeing through our own spiral arm, and we're seeing the next spiral arm over in the Milky Way. So stars are the most obvious feature of a galaxy, but they're not really what I'm going to be talking about today. I'm going to be talking about the matter that lies between the stars. We're told that space is a vacuum, Yes, it's a much better vacuum, probably a million times better than any vacuum we could get here on Earth, but it's still not completely devoid of matter. So in a volume, say, something like the volume of this soda can, there might be perhaps a dozen atoms of hydrogen. If you're very lucky, a single grain of dust, and I'll tell you about dust later. It's still not completely empty. And the volumes of space are so enormous that it still stacks up to quite an appreciable amount of matter between the stars. Probably about 10% of the mass that you see in all the stars, there's about 10% of that mass in gas lying between the stars. So tonight's talk is not just about the stars, it's about the space between the stars and the matter that lies there. Some of it is left over from when the galaxy formed, 11, 12 billion years ago. Some of it has been cooked in the centers of stars and then flung out at the end of their lives and mixed in. And mostly it's hydrogen and helium, mostly hydrogen, a little bit of helium, and an even smaller amount of heavier chemical elements. And this interstellar medium, as we call it, is of fundamental importance. This is the reservoir from which stars form. And it's not just the reservoir from which stars form, but also any planets around those stars and any life forms on those planets as well. So you all originate from this matter that lies between the stars. Now, here's my schematic of a starry volume of space in our galaxy. Now, not all this gas is apparent. Throughout the galaxy, there's a very hot, very sparse medium. It's so hot, it's giving off X-rays. And to all extents and purposes for this talk, we're going to ignore it. It's invisible. It's transparent for what we're talking about today. There isn't much matter in it, but it fills most of the volume of space. Embedded within that are colder clouds. And embedded in those are even colder clouds. Now, these diffuse clouds are denser. They've probably got an equivalent amount of mass in them, but because they're much more compressed, they don't occupy so much volume. And most of them lie in that flat disk of our galaxy. And these clouds are so cold that maybe most of the atoms in them, it's mainly neutral hydrogen atoms, that any light, any radiation they give off, we could only detect with radio telescopes like the ones down Barton Road. So again, this is largely invisible for the sake of tonight's talk. However, when these clouds are close to a heat source, they get heated up. They get heated up to temperatures of thousands of degrees. And at that point, if you pump that much energy into atoms, they begin to glow by their own light. And they glow and become visible. And those are the nebulae that we're mainly going to be concentrating on today. So along the spiral arms, you've got those bright blue stars. So when we look at a galaxy, you can see that the spiral arms are traced not just by the bright blue star clusters, but by pink clouds of gas. And if we zoom in just on the corner of this bit of this galaxy, you'll see that the gas surrounds clear blue star clusters. This is an external galaxy. Again, we have many examples that I'm going to be showing you tonight that lie much closer to us in our own galaxy. One such is the Rosette Nebula. And I'm going to be coming back to that in a minute. But I'd like just a little diversion about the images themselves and about the colors that we're using, because it's often a question I get asked. You will see in all the galaxies, in nearly all the images, a lot of these nebulae that I'm showing you are pink. Now, and just to stress, I'm sure I don't need to say this to this very erudite audience, but nebula is the Latin for cloud. So really, I'm just discussing clouds in space, and we call them by this name, nebulae. So this cloud is glowing a characteristic pink. And what you'll find is that most of the clouds and images that I show you, pink or reddy pink is going to be a dominant color. And that's because it's being emitted by hydrogen atoms. And if you excite hydrogen atoms so that they glow with their own radiation, they glow this pink color. So let's just talk a bit about color and what it teaches us before we get on to the rest of the beautiful images. Astronomers have to be incredibly clever. Well, I guess I'd say that anyway, but you've got to realize that we can explore our own solar system, but anything outside our own solar system, the only way we learn what's out there, how it behaves, is through the light it emits. And so we have to learn about stuff by analyzing and interpreting that light. Now, clearly, from images, we can get a distribution of the light and the matter emitting it. But the colors can give us further information. So again, this is a very simplistic level, but just to give you the idea that a star like our sun, it emits all the colors of the rainbow. And I'm going to concentrate on the optical waveband. So again, if you're familiar with these units, we're going from 400 nanometers. So this is short wavelengths. These are blue colors up to about 700 nanometers, which are red colors. And the sun emits in all colors. And that's going to be true for lots of stars that you'll see. They shine nearly all colors. Some are a bit bluer than others. Some are a bit yellower. Some are a bit redder. But they give off optical light at all wavelengths. The same is not true about some of the gas atoms in these clouds that I'm going to be talking about. So inside an atom, at the very core, there is an atomic nucleus. And that's surrounded by a cloud of electrons. And if these atoms are irradiated, you've got energetic ultraviolet light shines on these gas atoms, they can absorb the photons and borrow the energy. And the way it works is perhaps some of these electrons in the cloud may shift their position, their energy levels in that cloud of electrons. They more or less borrow the energy for a while, and then the atom emits the photon again and emits color. That's how the atom glows. The end point of what I'm trying to say here is that the color or the light that the atom radiates, once it's absorbed the energy, played with it a bit, and then gives it out again as a photon, that light is very much determined by the structure within the atom. So if you heat different atoms of different elements, and you give them energy, then they glow different colors, and they glow characteristic colors. So for example, if I heated a cloud of hydrogen, and again, we've got the scale of wavelength here from 400 to 700 nanometers, so blue to red, they just give off discrete photons of specific colors. And because it's to do with the energy levels of these electrons in the clouds, they can only give these certain colors. So if you see lines at 656 nanometers, you know that's a characteristic color of hydrogen, and this is the one that you'll see all the images are colored pink. If there's helium there, it'll give a different set of lines. If you've got elements of mercury or carbon or nitrogen or neon or sulfur, they all have a characteristic fingerprint in terms of the colors they emit. And which of these lines, which of these colors are strongest, we can use not just for what chemical elements are there, but ratios or specific patterns in these lines tell us the density and the temperature within the gas. And so astronomers use something called a spectrum, which is taking the light from the distant objects, plotting against wavelength the intensity of these lines. We have something like this. Here's the light from stars. You're plotting wavelength against flux, and you've got discrete spikes where it's lots of just a tiny little band of color, there's lots of light, and those are from specific elements of gas atoms. So here you've got oxygen, neon, hydrogen lines, oxygen, and here's the very strong hydrogen line that glows pink. So the reason I'm telling you this is that when we take a Hubble Space Telescope, for example, image, it's not just like the camera in your digital camera. We isolate light from specific bands. So say I'm interested in how hydrogen is distributed. Maybe I just want to select this tiny bit of color and just pick out all those gas, try and pick out the light from just the hydrogen atoms. Then maybe I'm interested in the oxygen, and I might take just that tiny little chunk of the spectrum and just pick out all the light that the oxygen atoms are giving off. And that way we can deconstruct where perhaps the chemical atoms are and where there's ratios between the lines. So for example, here's a nice wide filter. So we're isolating the light just in the wide green, centered around sort of 540, 550 nanometers. Pretty boring, lots of stars. Let's take a blue image, wide blue, so wide filter. Again, lots of stars, not very different. But then we take a very small filter. We take a narrow filter centered on the red, and this is where the hydrogen gas emits. And suddenly you can see all the hydrogen atoms in, this happens to be a supernova remnant here. And then we colorize each of these black images and add them together. And so the net result, you color the green one green, the blue one blue, the red one red. You end up with a composite image, which then recreates the natural colors. And I will say that nearly all the pictures I'm showing you tonight are real images of space. There may be one or two artists' impression, and I'll try and remember to tell you about them. The other thing is that a lot of the pictures I'm showing you, I try to pick out ones that are natural color. Not quite true color, but generally natural color. And so they're colorized so things are apportioned the correct color that they're emitted in. So we can do tricks like this, say, here's a bit of a gas cloud I'm going to show you later as part of a supernova remnant, and again, I'll tell you about those later. But we can isolate in a blue filter the light from oxygen atoms, light from nitrogen atoms, light from hydrogen atoms, colorize them as we like, stick them together, and you immediately get from the colors the distribution of the atoms within that cloud. There are times, though, when we play a little fast and loose with the colors. And that's especially true when we start getting right the edges of what we normally detect with our eyes. If you want to look at an image with your eyes, you need to be able to see the colors in it. So, for example, here's a beautiful nebula. There's an image taken in wide green. That's picking out the light from the stars. We have an image of a tiny bit of red. That picks out all the light from the hydrogen atoms in the cloud. But then maybe we take an image in the near infrared. It's kind of off the scale. It's over here. It's not like we can pick up with our eyes. So what color do we color it in our composite image? We have to cheat a bit. In that case, we shift all the filters down. In the colorizing, maybe we say, oh, we know it's green, but what we're going to do is we're going to color it blue. We know hydrogen's really red, but we want to color the infrared red. So we just slip it down a bit, make it a little bit sort of orangey red, and then we can then safely color the infrared red and then combine the images to get this. So what you see, it may not be accurate, but it is a fairly faithful representation. Things may have been slid down the spectrum a bit, but you still see what's bluer and what's redder. And then you get your final image like this. So most of the colors are representative of what we see. Now, of course, if you flew out there, you might see colors approximate to this. You'd have great difficulty perhaps seeing all the structures because you mix this light in different bands. We can have long images that pick out the faint gas clouds, short images that pick out the bright stars. So we might play hard and fast with the contrasts to kind of accentuate the very faint structures. And the other thing is if you try to look at this through a telescope, you would have great difficulty seeing these colors with your eye because the cells in the retina that are sensitive to colors, faint diffuse structures, the rods are not sensitive to colors. So it's always disappointing looking at these nebulae through a telescope because they appear just white. You're not picking up the colors. And so relax, and you're going to see them much better tonight in these images. So let's go back to the science, right? We've had a bit about the images. Here's the Rosette Nebula. At the core is a young cluster of stars. Remember, this is astronomy, so young is 4 million years old. They've collapsed down under gravity from a big cloud of gas and dust. And what you see surrounding it is the remnants of that cloud. Star formation isn't 100% efficient. There's matter left over in the gas cloud once the stars are collapsed in the dense core. And the light from these stars, the energetic light from these stars, is radiating the atoms, causing them to fluoresce. And it's mostly hydrogen, so you've got this pink color. Also around the star cluster, you'll see there's like a bubble. They've got their own little cavity. And that's because the stars heat up the gas next to them, hot things expand, and they create this bubble. There are also energetic winds from the surface of the stars, which eat away at the clouds, as we'll see later. And so all these star clusters you'll see, they'll have the surrounding gas cloud, and they'll be in their own little bubble. And just a word about scale. From one side of the Rosette Nebula to the other is 100 light years. Now, some of you may not be familiar with light years. Despite the name, it's a measure of distance. It's how far light travels in 1 year. Now, light's the fastest thing there is. It travels at 300,000 kilometers per second, and it travels 9.5 million kilometers in 1 year, and we just call that a light year. So it takes light 100 years to go from one side to the other. So don't think these are tiny little things around stars. These are vast structures. So we've got the stars. I've told you about the gas. The last ingredient is dust. And by dust, I don't mean like what you may find rolling under your bed at home. It's not the dust that Philip Pullman has in his stories, which is what he uses to describe the idea of dark matter. This is actual small solid particles of carbonates and silicates, so it's like soot and sand. And these particles are mostly tiny. They could be about 1,000th the width of a human hair, up to perhaps a few molecules across. They're little solid particles. And if you like, perhaps about the size of particles in cigarette smoke. They're tiny. But if you get vast clouds of tiny particles, there's enough of them that they can obscure any background light. So when you look at this galaxy, you can see the nebulae. You can see the blue star clusters. You can also see dark veins along the spiral arms. That's not an absence of stars. There's a veil in between you and the background light. That's the clouds of dust blocking the light from the stars. And that's mainly comprised within the plane of the galaxy. So if we instead look at a galaxy edge-on, you will see that the dark layers of dust almost like cut the galaxy in two. And I'll remind you that you live in a galaxy like this, about halfway out from the center to the edge. So when you look at your galaxy, you're seeing edge-on like this. And so if you see the Milky Way, unlikely to see it like this from Cambridge, especially as this is taken in the southern hemisphere. It's slightly more dramatic because you're looking more towards the center of the galaxy in the southern hemisphere. Just to guide the eye, you can see the kind of shape of the galaxy there. But I hope you can see there are dark clouds even within our galaxy. There you're seeing these dust clouds in the disk of our own Milky Way, fully without telescopes, binoculars. In particular, up here, you have the Southern Cross. If anybody is familiar with the Southern Hemisphere, it's a very prominent constellation. And right next to it is the Coalsack Nebula. Again, you can see this with the unaided eye. It's a big, dark cloud that's blocking the light from the background stars. So this dust exists in with the gas. And it's more than that. It's mixed in together. And when you see a nebula, you see not just the gas clouds radiating, you also see obscuration by the dust. So here is a classic nebula. What you have to remember, there's a big diffuse cloud around it. You can't see it because it's radiating in radio. It's invisible. You only see the gas when it's close to a small star cluster. And then it's almost like a little bubble, a little blister that's broken through the cloud, if you like, and you're looking into a cavern where the inside is lit up by the glowing gas atoms, the glowing hydrogen. So if we zoom in further, you begin to see that there's dark shapes. And this is where the dust is mixed in with the gas, and it's blocking out the background light of the hydrogen gas. And if we zoom in even further, you see some of these completely opaque clouds. And these are the densest clouds in the interstellar medium. I say dense, they're still a lot less dense than the air you're breathing now. But the dust is mixed in with the gas. And because they've got so much dust within these clouds, not only does it stop the starlight, the background stars, the starlight getting through to us, it also stops the heat from those background stars from entering the cloud. So the core of these clouds gets incredibly cold. It goes down to a few tens, perhaps degrees above absolute zero. And at those kind of temperatures, the atoms in the cloud join up to form molecules. And these are known as molecular clouds. Deep within these, we have molecules not just of hydrogen, though that was obviously the most common, or water, carbon dioxide, carbon monoxide, we've got ethanol, we've got ammonia. Think of a complex molecule. We've probably found it out there in space. And the other thing you notice that this is kind of looking a bit shredded around the edges. It's sitting in quite a harsh environment, and that makes these molecular clouds suffer. So dust. We see it because it blocks out the background light. Now let's look at a very famous constellation. If it were clear tonight, you can go and see this in the southern sky. I hope you all recognize it as Orion. This may be how you would see it with your unaided eye, but if you then take a picture which is sensitive to all the hydrogen gas there, that's lying in this direction about 1,500 light years away from us. See, the whole constellation is encased, embedded in hydrogen clouds. And if we zoom in to a region around Orion's belt, there's a very famous nebula in a sword. But in a minute, I'm going to look at this region here. And then I'm going to just tip the image around on its side. This is the Horsehead Nebula, for obvious reasons. And you're looking at the edge of a dust cloud here. Note, there are more stars up here than there are down here. That immediately tells you there's something obscuring stars behind here. You see the edge of the cloud. Energetic light, winds from stars are shining down. They're making the gas glow, and you can sort of sense it boiling off. Except to the point here where you've got a really dense pocket of dust that's kind of protecting just this little pocket from erosion from the starlight and star winds. And that's the Horsehead. And that resists the erosion. And if I zoom in even further, we look at this in detail. This is what's known as the working edge. That's where the impact from the winds and the ionizing radiation from the stars eats into the clouds, provides a nice sharp edge. And already you can see perhaps a young star breaking out of this gas cloud, this gas and dust cloud. That's going to be your first indication that this is where stars are formed. You'll also notice that the stars that you see through the cloud appear red. The ones outside appear white. And so dust produces an effect on stars. It's the curse of astronomers. Any light that goes through a dust cloud is what we call reddened. And as the light travels through the cloud, the photons interact with the dust particles. And it depends on the wavelength of the light, the color of the light, and the size of the particles. But what happens is the blue light gets scattered by the dust particles preferentially. The red light can just travel through the dust cloud fairly unhindered. So this, for example, is why you see red sunsets, red sunrises. It's the particles in our atmosphere scattering the blue light. At midday, the sun is overhead. You're seeing it through the atmosphere. Maybe there's a bit of scattering. But down at sunset or sunrise, you're looking at it not just through more of the atmosphere. And of course, this diagram is not to scale. Hope you realize. You're looking through the denser part of the atmosphere as well. So there's more of this scattering, and only the red light makes it through, or the blue light gets scattered out of the path. It's the same reason you see a blue sky. That just reminds you what a blue sky looks like, in case we didn't have one today. When you look up at the sky, you're seeing the scattered blue light. So if I'm standing down here on the Earth and I look directly at the sun, I see all the light from the sun making it to me. But if I look up in the sky, I see all the blue light that's been scattered by the sunbeams going through other parts of the atmosphere. So in the same way that the scattered blue light makes the atmosphere visible to me, the blue light that's scattered by dust can also, it makes the stars that you see through it appear red. It also makes the dust cloud obvious. So here you have a dust cloud. I hope you can see there's sort of obscuration here, dark patches. As soon as it gets near this bright star, it's lit up. You see the scattered blue light. Near the famous Pleiades, they happen to be living near or moving past some dust clouds. These are blue. Okay, the stars are blue, but you're also seeing all this blue light that's scattered off the clouds. And here's one of my personal favorites. This is the bright star Rigel and a dust cloud next to it. And it's scattering the blue light. It's called the Witch's Head Nebula. Can you see her profile? Yeah, nose, mouth, nice witch's chin. So we can see the dust because it scatters, because it absorbs. And it also gives off its own light. Most of the images I'm going to be showing you are optical. Just going to show you a few infrared pictures. So you recognize here you have the edge of a dust cloud. Look, more stars up there, fewer down here, obscuration, edge of cloud, pink gas being ionized. I'm now going to move to the same picture, same region of space and the same scale. You're now going to see it in infrared radiation. Because what happens is this light, it heats, I mean, it's blocked from getting right to the core of the clouds, the densest part of the clouds, but it heats up the dust grains, heats them up to temperatures of tens, hundreds of degrees, where they start to radiate, not in the optical, but in the infrared. They're not quite warm enough to radiate in the optical. And so you can detect the infrared emission from the dust grains themselves. And suddenly all the dust structures become apparent. Should I do that again? I want you to look particularly around here and around here, and you will see, in the same way that I told you red light isn't affected by dust grains, that means that infrared light is even less affected by dust grains. So deep in here, there are star clusters. We can't see them in optical light, but their infrared light can travel through the dust, and we can see them there in the cloud. It's true about external galaxies. Here's a beautiful whirlpool-shaped spiral galaxy. You see the dark obscuration from the dust lanes. If I click to infrared, again, you lose the stars, and you just see the emission from the dust itself. And here's the optical, again, of the Pleiades. And if I move to the infrared, again, it becomes much more apparent, the radiation from the dust. And we're going to stick at the Pleiades for a minute. Here's the southernmost star, Merope, and I'm going to zoom into a tiny little region next to it. And by next, I mean it's probably separated about but just over 3,000 times the size of our solar system. Okay, so that's quite close. And if I zoom in on this tiny region with the Hubble Space Telescope, now the star Merope is up here, somewhere out beyond the wall, and you can see some of the scattered light from the star. But this little patch of dust, you can see it's been affected by the light and the winds from the stars. It literally is as if something's just gone whoosh over a pile of dust. The lighter, fluffier grains have got swept back more easily. The heavier grains have resisted this push. Sorry. So you get the idea that starlight and star pressure, star winds can sculpt and shape and push dust around. And nowhere is this more obvious than in this beautiful nebula called the Eagle Nebula. It's not actually obvious from this picture why it looks like an eagle, but if you zoom out a bit, it's more eagle-shaped. Now remember, this is like a cavern in a big, cold cloud. You've got a young cluster of stars, about 5 million years old. Their light's radiating exciting gas lining the walls of the cavern. And what you can see is that there are dark dust structures that are opaque. Now, if we zoom in on some of these, you can see they form these long pillars, and the size of these pillars, it's about 10 light years long from one end to another. And the starlight and the winds are having an effect and eroding the dust and the gas. But why do they always form those pillars? You see that they're very distinctive long pillar shapes, and you'll notice them a lot more in a minute. And this is to do with the nature of the radiation and the direction it's coming from. Imagine you've got a cloud of different densities of gas and dust. So here the darker pockets are the dark bits are meant to be the really dense pockets that resist the erosion. The lighter, fluffier stuff are progressively lighter grays. Now I'm going to switch on some young stars high up above the ceiling. The light's going to eat into the cloud progressively. Or it should do. It'll eat into the cloud. It erodes the lighter, fluffier stuff much more rapidly. And then the denser stuff acts almost like an umbrella, protecting the stuff beneath it. And underneath that umbrella, the stuff behind is not irradiated, it's not eroded, and you form these long pillar structures. And so if we go back to this image you've already seen, you can see it's like fingers always pointing in towards the star cluster all around the edge of the nebula. They're there in the Rosette Nebula. They're there in the Eagle Nebula, pointing in. And in fact, these three pillars form one of the most iconic Hubble pictures that you've seen. That's good. I thought you'd forgotten about the oohs and ahs. I'm glad they're there. And again, these are light years long, but even on the tiny scales, you've still got that sort of protective pillars, and they're all pointing towards the source of the radiation and the winds. If we zoom into the top here of this pillar, you get a sense of the gas boiling off. It's being lit up, it's being ionized, it's heating up, it's boiling off. The dust is getting swept off and away from the pillar. And what's left behind are the densest pockets, the coldest pockets, and they resist this erosion. And you can just begin to see them breaking free from the edges of the cloud. Just ringed a few to guide the eye. And if you want to see what happens to them, well, we have to go back to Orion and look at those little sort of cocoon shapes at the next stage of development. So back to Orion's belt, there was the Horsehead Nebula. We'll go down to the Great Nebula in Orion's Sword. This is a massive region of star formation. It's a huge stellar nursery, and deep within there, there's a cluster of stars. Let's move to the Hubble Space Telescope picture that just takes in a little bit of that nebula. Again, think of this as a large cavity that's been excavated by the winds and light from these stars. So again, on the same scale in the infrared, you can see through the clouds, and you can see the young star clusters lying at their core. And some of these are only a few 100,000 years old, very young. And they're blowing and shaping the gas around them. But if we close in on those stars, or the four very obvious ones we see here, now, that's a little bit saturated. I'll just change the contrast a bit, because I'm not so interested in the stars. I'm interested in some of the structures of the dust. And you can perhaps see there are a few funny objects. Let's just ring them and blow them up. Those are those cocoons at the next stage of their development. We think these are planetary systems in formation around young stars forming from these gas clouds. Here's a schematic. I don't think I need to tell you this is an artist's diagram, do I? So if you have a large cloud of gas and dust, it collapses under gravity, especially where it's densest at its core. And if things fall under gravity, they heat up, they gain energy. And so matter rains into the core of the cloud until at some point it reaches temperatures of, say, above 15, 18 million degrees, and a star is born, and the process called nuclear fusion can begin that makes the star shine. But again, star formation isn't 100% efficient. There's lots of stuff left in the cloud around it that hasn't got used up in the star before it got switched on. And because it's spinning, this settles down into a disk. Now, this disk eventually, we think, goes on and forms a planetary system over perhaps the next 100 million years. Perhaps this is how our own solar system started 4.5 billion years ago. With these objects in Orion, we call them proplids, by the way, short for protoplanetary disk. We think we're catching them in about this stage. There's a very young stellar object, and it's surrounded by like a donut or a dust ring. And again, artist's impression. I wish we had pictures this good of the proplids. But you've got a young stellar object, and then you've got a very dense cocoon of matter around it, including the obscuring dust. So look again at some of these proplids in Orion. Some of them are very conventional. Some are very misshapen. And just to remind you that a solar system like ours, we think, was lucky, was formed in a fairly isolated environment. These little proplids are forming right close to the strong winds and radiation of young stars, and it's blasting them. In particular, if you look at the ones very close to the massive 4 stars in the center, I'll just ring them and give you a sense of their direction. They're almost like wind vanes being pushed out. And there's a lot of argument amongst scientists about whether proplids like this will eventually go on and form solar systems like our own, or maybe just a reduced number of planets or a different kind of planets. Maybe some of the solar systems had very different kind of formation processes between the cocoon and the planetary system. So I've told you how these nebulae are the places for star birth, but they're also intrinsically associated with the death of stars. And you get all kinds of stars out there. You get yellow stars like our sun, lots of the blue stars that I've shown you in some of these star clusters. And a whole of a star's life is a battle against gravity. Gravity wants to pull it in. And the only way it can resist this is by the process called nuclear fusion at its core, where it fuses progressively heavier elements and obtains energy that supports it against gravitational collapse. So a star like our sun will start by fusing hydrogen atoms into helium. And it'll do this for perhaps up to 12, 15 billion years of its life. But at some point, it's going to run out of the fuel where it's hot enough to do the fusion in the core of the star. And at that point, it's not hot enough to burn perhaps heavier elements, and it can't any longer support itself against gravity. And when that happens, the core of the star collapses. It collapses down. Now remember, things that collapse down under gravity get hot. So the core of the star collapses down, heats up, and drives away the outer layers of the star and forms something looking a lot like this. Now this is a planetary nebula. It doesn't mean it's got anything to do with planets. It's just the name the 18th century astronomers gave them when they first started observing them in the telescopes, because they were sort of round and disky. Now here you're really looking at a bubble that's been thrown off a star. This is the famous Ring Nebula. At the center here is the core of the star collapsing down to become what we call a white dwarf. It's heated up. It's going to glow for a long time, and its radiation is exciting the gas layers that have been blown off the star, causing them to give off radiation. These are going to expand away into space over the next few thousand years and cool off and fade. So these are fairly transitory features. What you may also have noticed within the structure here are dust obscuration, dust structures. And so this is, and as well as some of the infrared observations, shows us that we think the dust that we see endemic throughout these galaxies is forged perhaps in the late stages of a star's life. Before it goes this catastrophic collapse, it swells up to become something called a red giant. And the chemistry and the temperature and the outer layers of this is ideal for forming dust grains that then get expelled when the outer layers of the star blow off. And there are myriads of these beautiful nebulae. This is a fairly conventional one. It's about a light year in diameter. Here's a much younger one, about 0.2 light years in diameter. It's called the Spirograph Nebula. But again, the source of these weird structures isn't obvious. And if you read about this in astronomy books, you have a very conventional view. The star center goes crump, outer layers go off in a nice expanding shell. In practice, it's rarely that beautiful or that simple. Here's a very strange planetary nebula. It's got several bubbles. It's got like 11 different shells. It's almost like it's thrown off a layer of material about every 1,500 years, and it's done it about 11 times. And not content with that, it's emitted jets and winds from the white dwarf. To understand the endpoint of a star like our sun is not as trivial as you might think. There are very complicated physics going on. It's not in creating these beautiful structures. And you don't just get ones like this, you get even more complicated ones where the emission, the outer layers seem to get driven into a bipolar shape. And here, for example, it's a beautiful picture from the refurbished Hubble Space Telescope. It looks like the star at the core perhaps threw off an outer, very dusty, very dense layer, maybe a few thousand years before, and that's formed a donut or has been blasted back into a donut, and the other stuff has been ejected. It hasn't been able to go in that direction because the dust donut has blocked it, and it's expanded, and it's been shaped by this initial bit of dust. And you get systems where perhaps they were binary stars, or maybe there were strong magnetic fields in the progenitor star. You get very complicated structures and outflows. But if you have a star that's much more massive than our sun, say above 8 solar masses, the endpoint's somewhat more catastrophic. It's hot enough to burn beyond hydrogen to helium. In fact, it can start fusing elements right up to iron. At that point, you can no longer get energy out. Bigger stars, more massive stars, are the blue stars, because they've more mass, they've got more gravity, they've got to produce more energy to resist that gravity. They've got to burn hotter, and in physics, hotter things are bluer. So if you see a blue star, it's a massive star. And not just that, you know it's a young star, because even though they start off with much more mass to begin with, they burn through it at such a prodigious rate. They have lifetimes of only tens of millions of years. And so if you see a blue star, it's a hot star, it's a young star, it's a massive star. And when these reach the end point of their lives, when they finally have fused into iron in the core, they throw off their outer layers in a much more dramatic explosion. Here's an example of one that was, the explosion, it's called a supernova, was observed by Chinese astronomers in 1054. This is how it appears now. These filaments of the outer layers of the star are still expanding away at about 1,000 kilometers per second, enormously fast. And these filaments comprise not just the outer layers of the star, but as they expand, they sweep up the interstellar medium before them. The blast wave, there's lots of energy in the blast wave. It can excite the atoms in the gas, both the stuff that's thrown off the star and the stuff in the interstellar medium. It all gets mixed up together, it all gets compressed. And as it cools, it produces these glows and what we call these supernova remnants that glow for thousands of years. The core of the star, so say in this case, the core of the star collapses down, it gets squeezed by gravity until such a point that even the atomic structure gets affected, and protons and electrons get squeezed together to form neutrons, and neutrons don't like being squeezed, and they resist it. And that's when you have a neutron star. If you start having a much bigger star, or the original star was much more massive, say about 25 solar masses or more, then you can't stall the inward pull of gravity, and that's the point where you get a black hole. So these supernova remnants usually mark the points where there are neutron stars or black holes, these exotic objects, the endpoints of stars right at the core. And of course, these are chemical factories. You've got all the elements that were cooked up in the center of the stars. During the supernova explosion, there's a flood of neutrons that bathes all the atoms. Some of these atoms can instantly transmute to much heavier elements than iron. So a lot of the heavy elements are cooked up in the supernova explosion, as well as being discarded from the cores of the stars. And these then get thrown out into space, mixed up with the primordial hydrogen gas, and seeds the gas around it with these heavy elements. And this is important because those are the gas clouds that later go on to collapse and form new stars. And so all the carbon and nitrogen and iron that's on our planet, in our bodies, has gone through this process of being formed in a star, mixed up into a gas cloud that then later collapses to form our sun and the planets. Because all of this is going on at once, and in the same region. Here's an example. Here's the star cluster. You can see the gas cloud around it. You can see some of these pillar structures. There's one star on the edge here. Maybe this is the one that was the most massive. It's about to go supernova. You see, it's kind of thinking about it. It's throwing a few preliminary layers, thinking, yeah, shall I go supernova? Yeah. So that's about to go supernova very soon. It's reaching the end point of its life. But still within this cloud, you have some of those very small dark molecular clouds waiting to fall together and form stars. And you also have perhaps a couple of proplids down here, beginning protostars forming within a cocoon. So all of this happens simultaneously in the same environment, and one can affect the other. And so for my final point, I want to just talk about the process of star formation. Because I've told you there's lots of gas clouds in our galaxy. They've been hanging around for billions of years. Why is star formation still occurring? And if you have a gas cloud of a certain size, it might have little bits within it that are slightly denser than others. So maybe there's a region here where the atoms, the particles in the cloud are slightly closer together. Gravity is stronger the closer you are to something. And so these pockets begin to collapse down under their mutual self-gravity. And gradually you might get condensations forming, denser regions within the cloud. And then these, of course, have a stronger gravitational pull and particles around them, pull them towards them, and you start a runaway process of gravitational collapse. So you think, yeah, all gas clouds, none of them are perfectly homogeneous, they're not all perfect density, some of them will, why haven't they all collapsed? Of course, not all particles are stationary. Anything that has a temperature that isn't absolute zero, all the particles, all the atoms are just jiggling a little bit. They're in perpetual motion. The hotter the gas, the more these particles are moving around. So even stuff that's at hundreds of degrees above absolute zero, the particles are jiggling all the time. You all mesmerized yet? I'll stop that. And these motions, we call it the thermal pressure, the thermal motions of the particles, can give the particles energy to resist the inward pull of gravity. So any gas cloud of a given size, whether or not it collapses to form stars, depends on the balance of these two physical processes. Okay, I mean, there are things like magnetic fields and rotation that might also inhibit collapse. So a very simplified idea here. But if you have a gas cloud, whether or not it collapses to form stars depends on the balance between the gravitational force wanting to pull it in and the thermal motions of the atoms that resist this force. And if effectively, for any one cloud, that's a balance between density versus the temperature. So if star formation is going to happen, one of these has to change. You can have a large gas cloud, and it lives out there in space for billions of years in what we call like an equilibrium state. It doesn't collapse. It's too hot, perhaps, or it's too sparse. It doesn't fulfill the criterion for gravitational collapse. It only starts to collapse into stars if one of these two values changes. Now, it's hard to change the temperature of a cloud suddenly. There's lots of energy coming in. Things don't cool down fast. The one thing you can change very rapidly is its density. And if you just squeeze gas clouds a bit, you can increase the density, maybe push them out of this equilibrium state, tip them over the edge so they start collapsing to form stars. And this, again, is going to happen. Remember, you want the coldest and you want the densest places. You're really looking within these dark, dusty molecular clouds. And as soon as you squeeze them, give them an outside kick, they start to collapse, and you get runaway collapse to form stars within those clouds. So if you leave a cloud long enough, maybe it'll get a gravitational tug from another cloud, a star. Maybe something will trigger it to form collapse. But there are other external things which can accelerate this process. The most obvious place we've seen for young star formation is in the spiral arms of a galaxy. Whole clusters of young blue massive stars line the spiral arms. Now, I won't pretend we fully understand this. Spiral arms are a feature that we see in all spiral galaxies through the disk. And what we think is happening is that you have, we call it a density wave, a wave of compression, if you like, moving through the disk. And as it moves through the disk, it squeezes the gas just that little bit, triggering it to form and collapse stars. And where this density wave comes from, again, you might get another astronomer here, and they may give you a completely different view of this. It's one of the things we're really not very certain about in spiral galaxies. But perhaps it could be the fact that all the gas clouds, all the stars in orbit around a spiral galaxy, they don't all necessarily orbit in perfectly circular orbits, slightly squished circles we call ellipses. These don't all necessarily orbit in phase. And you may get twisting and bunching of these orbits. And you naturally get a spiral shape from the squeezing of these different clouds and the proximity of these clouds. And so we think that could be one place where you get, one reason why you get these compression waves that travel through the disk, causing collapses of star clusters in their wake. And on a much smaller scale, here's a young star. It's only about 2.5 million years old. You can see it's excavating that bubble around it from its winds, from its light. And as it does so, it's pushing material back. And if we move to a view for the new Herschel Space Observatory of this in the infrared, you can't see the star because it's too hot to give off infrared emission. But you see the light from the gas clouds and the dust around it. And you can see that it's pushing back around the edges of this bubble, and just here, there's a new star about to form. And that has been triggered just by the squeezing of the winds and the light from the star. But the final nebula I'm going to show you is where we see this happening sequentially across the nebula, this whole cause and effect from dying stars to new stars being born. This is called the Heart and Soul Nebula. Not quite sure which is the heart. You might guess that that's... Sometimes you can see what they're on about, can't always. This is a mix, just to confuse you all now, this is a mix of infrared and optical. So the blue is kind of where the optical stars are. The green and the red are in the infrared, and they show you where the dust is. The red is hot dust. The green shows you the green dust. And I'm just showing you this because it's clearer where all the structures are, the invisible structures within the cloud. Actually, you have seen part of this nebula before. There's a little region over here. Well, actually, just zoom in on what I think is the heart. Somebody may also say it's the soul. And we'll just look at this region here. You have seen this. This was the first infrared picture I showed you. And again, just to give you a sense of comparative scale, if I showed you the pillars from the Eagle Nebula to scale, they're about that size. So the picture on the right is taken with a Spitzer Space Telescope that works in the infrared. The picture on the left is taken with the Hubble Space Telescope. You've got to realize there's a bit of one-up-personship between these space telescopes. Now, when this Hubble image was released in 1995, great acclaim, fantastic image. They were very pleased with it, and it became known as the Pillars of Creation. 10 years later, when this picture from Spitzer is released, they decided to call it the Mountains of Creation. There you go. So here we have the Mountains of Creation. You've already met them. They're around the outside of one of these nebulae. But if we map throughout this nebula, we can see a time progression of causation and effect. So right in the center of the nebula, right at the very heart, actually you don't see a lot. There are a few sparse hot stars. Some of these are foreground stars, so the really big, bright ones are the massive stars. Now, these are all that remain from the original collapse of stars from this cloud. They were originally in clusters, but you know, so much has happened, so much time has gone by. All their cohort have gone supernova, and these are just the stragglers, the survivors, the ones that weren't yet massive enough to go supernova. However, those clusters, when they were born, they had the gas cloud a lot closer to them. Their light and their winds pushed on the gas cloud. They pushed it away from them. They squeezed the gas. And they triggered a second generation, either from the squeezing or from the actual supernova explosions. Because remember, these are huge blast waves that ripple through the gas. The combined effect squeezes the gas and causes the next generation of stars to form. Now, these are still in fairly young star clusters. So you can see that these may be a few million years old, perhaps 4 or 5 million years old. And indeed, when you look in the infrared around some of these star clusters, there are a lot of proplids in formation. Again, poor little proplids being battered by the winds and radiation from the stars, but nonetheless, some kind of planetary system forming around these stars. But that's not enough, because the winds and the radiation from these stars are now pushing on the boundaries of the current nebula. And as I showed you from the first near-infrared image, these are squeezing the gas and forming the next generation of star clusters to be born. These are still deep within the dust clouds. They haven't broken free. They haven't excavated their bubble. But these are the next star clusters that are going to emerge in this nebula. And so you have a progression of at least 3 generations of star formation, the first one triggering the second, triggering the third through a nebula. And you see the sort of generational effect within one cloud. Okay, I have shown you a lot of pictures this evening. I didn't know quite whether I was going to get through them all. There are an awful lot I didn't get a chance to show you. I do want to stress that I have quite shamelessly pilfered all these images from work of many of my colleagues all around the world. And all these images you can access on the web. And in fact, if I have inspired you to go and find out more about the science and beauty of nebulae, I give you just 3 things that you could go and look at in your favorite search engine. So the first one I recommend, it's called Astronomy Picture of the Day. And this is the one website that everybody in my department, whether it's the highest professor or the lowliest secretary, or should I say the lowest graduate student, but I don't, 'cause some of them are in the audience. But that is the first website everybody goes to. It'll have a picture about something about planetary geology or space science or some of these nebulae or distant galaxies from a range of wavebands with just a chunky little paragraph of very accessible text. So that is a new picture every day. It's been running for about 10, 15 years. There's a huge backlog of images that you can go and scroll through. And you can do searches for your favorite nebula, type of object, everything like that. Second site I thoroughly recommend, Hubble Heritage Gallery. Put those words into your search engine. You can access all the Hubble images, the really famous ones, some you may be completely new to. And again, they give a very accessible page of text about, again, understanding the science behind what you're seeing. And you'll find many of the pictures I've used have come from there, and there are many more to explore as well. And finally, the images I've shown you tonight, well, most of them have come from the Spitzer Space Telescope. So there's a similar image gallery there that you can access. But I will flag that many modern telescopes, the new telescopes, the Herschel Space Observatory, the Planck Telescope, the next generation's space telescope, all work in the infrared. There will be growing archives of new images, of infrared images for you also to explore. And I hope you have fun doing so. Thank you very much.
When I was a kid, I think we had the general impression that space was space and that it was all empty. But it's clearly full of crud, hydrogen and helium and soot and sand, water and alcohol, a bit like Regent Street on a Saturday night. And it's all blowing and it's all glowing, and it's got implosions and explosions, and there are births and deaths, and it's all to do with the transmutation of elements. The beauty of the images that these space observatories have given us is just breathtaking. But also, I thought that the explanation that Carolyn has given us is also breathtaking. And it's rather satisfying because we started the series with particularly Robert May and Frank Wilczek explaining to us how simplicity in thinking, mathematical and otherwise, has helped to explain our understanding, inform our understanding of the universe. And we've ended with Carolyn telling us how the use of science helps explain the beauty, but the ideas and the beauty all interact. So very many thanks, Carolyn. That was very much appreciated, especially at 5 days' notice. Can I just say some thanks for this series? It was organised by Lauren Arrington, Zoe Leinhart, Philip David and Jessie Homans. It was supported financially, as always, by the ever-generous Richard and Anne King, whose generosity is just beyond praise. And, of course, it was supported by large numbers of people at Darwin College who muck in and make it all work. So many thanks to all those people. This is 2011. Next year is 2012. What's 2012? Wish it's life. Quite a home team. It's my last year in this role. And I thought, since there are so many fine speakers and fine academics and the rest in Cambridge, we ought to give them a bit of a burst. So, same time next year, I mean. See you here. Thank you.